So today I'm going to prove Euclid's theorem and right triangles. So basically, what is Euclid's theorem? Say I have a right triangle here, ACB, and angle C is the right angle. I've labeled it, and I drop an altitude onto the hypotenuse AB from C. So I just drop this altitude here. Just assume that it's a straight line, and we have this 90-degree angle. It's an altitude, and we call this point D. Then basically, the Euclid's theorem states that we have, so firstly we have CD is the geometric mean of AD and DB. So by geometric mean, I mean you take the product of two numbers, and then you take the square root of that product to get their geometric mean. So AD times BD, the square root of AD times BD is a geometric mean, and it's equal to CD. And then also the second rule is that we have AC is equal to the geometric mean of AD and AB. And then the third rule states that we have BC is equal to the geometric mean of AB and DB. So basically, we're going to prove this today, and how are we going to prove it? So the method I find most easy is using similar triangles. So where are the similar triangles? Well, there are three, and we have ACD. We also have BCD, and we have the largest right triangle, ACB. So these three triangles are similar. So let's just prove that first before we prove the Euclid's theorem with it. So basically, with the similar triangles, we can prove them using angle. So basically, we want to find that. So if two angles in a triangle are the same, then they're similar. So we already have one angle to our advantage because we have the right angle in every single triangle, right? We already have one angle. We just need another angle. So that's fairly easy because these three triangles are all in one right triangle. So basically, we can first prove that ACD is similar to ACB. So ACD is similar to ACB because firstly, we have this right angle, so we don't have to write that. We already know, it's obvious. And we also have, so this angle A is equal to itself, right? So angle A is in both triangle ACD and also in triangle ACB. So we can use that angle as an angle similarity reference. So we have triangle ACD is similar to triangle ABC. So via AA, angle similarity, and you have to pay attention to the corresponding sides and angles. So because they determine the ratio, which we're gonna have to use later on. So basically, now you prove that we have 2 out of 3 similar triangles. We just need to prove that triangle CDB is similar to triangle CDB is similar to triangle ACB. So we can still use this angle here, angle B, because it's in both CDB and ACB. So we have triangle CDB is similar to triangle, so CDB is similar to triangle ACB. So once again, we should pay attention to the corresponding sides and points. So after we prove that both the 3 triangles are similar to each other, then now basically what we should do is we should use the common ratio between the side lengths, because actually these rules are all about side lengths, right? So we can just use the common ratios and modify them a bit to get what we want. So firstly, we want to prove the first rule here, which is CD is equal to root AD times BD. So we want to find 2 triangles who are similar when we already have 3. So we need to pick 2 out of 3 triangles which contain sides CD AD and BD. So once we draw the side lines, it's kind of obvious which two triangles to pick. So we're just gonna pick triangle ACD and triangle BCD. So what do? So we know that the two triangles are similar, so we can use the side length ratio. So we have AD as the shorter leg is also, so AD over CD, because CD is the shorter leg in the corresponding triangle, AD over CD is equal to, so the longer leg over the longer leg, which is CD over BD. So if we just multiply both sides by CD, we have CD squared is equal to, and we also multiply both sides by BD, you have CD squared is AD times BD. So we just take the positive square roots of this. So we have to take the positive square root, not the negative, because side lengths have to be positive in order for things to make sense. And we've proved our first rule. So the other two rules can be proved using really similar manners. So basically we know that we want to find a triangle. Actually, we want to find two triangles in this triangle ABC, which includes sides AC, AD, and also AB. So now we should pick triangle ACD and triangle ABC. So what happens after that? So after we choose our 2 out of 3 triangles, we basically use the ratios again. So we have CA or AC, let's just write it in the same order. So AC, which is the hypotenuse, over the other hypotenuse, AB, is equal to, so AD is the shorter leg, right? So we have AD over AC. So we have AD over AC is equal to AC over AB. If we just multiply both sides by AC, and then we take the square root of both sides, we have AC is equal to AD times AB. So that's just our second rule proven. So the last rule, you probably know what to do. So you look at the side lengths. This involves BC, AB, and also DB. So we choose triangles DCB and triangle ACB to work with. So BC is the hypotenuse for BCD. So we have hypotenuse over hypotenuse is equal to, so we haven't included BD yet. BD is the longer leg. So we have BD over, so longer leg over longer leg, BD over BC. So these two are equal, and if we just multiply both sides by BC and we take the square root of that, we have BC is equal to AB times DB. So we've proved our 3 rules in Euclid's theorem for right triangles. So I hope you find that useful. Thanks.